Is there a pointer? Okay. Okay, so good morning, everyone. So today I'd like to talk about this abstract topic of optimization. So a little bit slightly mathematical, but then I'll keep it at a low level. So this is not really optimization as the topic said. So it is an introduction to optimization. It's a really low level topic. I mean, at a very basic level that I'll talk about. So here is a quote and here is a picture. I'll let you read the quote. But does anyone know who this person is and who was Euler? So who said Euler? He's a mathematician, right? So if you know the famous uh, formula e to the I pi is plus 1 is 0. So this was the guy who invented it. So and he says, since the fabric of universe is most perfect and the work of a most wise creator, nothing at all takes place in the universe without some rule of maximum or minimum. So that is how much importance he places on optimizing things and so on. And that's what we'll talk about today. This is Euler, as someone correctly pointed out. So here is a practical optimization problem that you might be interested in. So on the x-axis, you have the lecture time, the time I'll talk today, maybe an hour. And on the y-axis, you have how bored you're feeling right now, right, with the topic. And the green curve is how much you understand, and the blue curve is your boredom, right? So, and then if you want to optimize, what would you do? You would want to stop listening at a point where you don't get bored, but you maximize your understanding as well. And from this picture, that would be something like 8 minutes, 25 seconds for a talk in summer school on an average, probably. The star indicates that does not apply to this talk though. Okay, so let's hope that it is on the right side of that. So let's go on. So what are some practical problems or some reasons why optimization is important? Why should you even care about? And what is optimization at all that we are talking about? So here's an example. Let's say you are here and you want to throw a ball up, and what you're trying to measure is, with respect to time, how much height that this ball travels, right? So you want to kind of track the trajectory of the height of this ball with respect to time from point A to point B. And any guesses as to how this trajectory will look like? For example, can it look like this? How many of you think this is a right curve for this time versus height? No? So what curve should that be? Which parabola? Why red? How did you guess it's red? Viscosity? Okay, so there are too many ways. So you can use Newton's law and all those things to figure this out. But then I'm going to give you a different perspective as to how this works, right? So this is by Law of Mopitus. So this is a famous scientist. So what he said was, so you can look at something called action for a path at a point, right? So this ball travels from point A to point B, and at every point you can define something called as an action, which is just the difference of kinetic energy and potential energy at that point. And then for a path, you just sum up or integrate your action over the entire path, right? And now surprisingly, nature chooses the path of least action. We don't know why, right? But that's how nature does it. So when you throw a ball, well, why did it not go in the green line? Why did it not go in the yellow line, right? So these are philosophical questions. But then what nature does do is it fixes the path of least action. So this is an example in nature how nature optimizes itself. So here are a couple of more examples. So when you take 2 points and then you shoot a beam of light, it travels in a straight line, right? So it takes the path of the least time. And this Occam's razor says, it's a philosophical argument saying that if you have competing hypotheses to solve, so you are Sherlock Holmes and then you have a problem to solve, and then there are lots of hypotheses which kind of might give you solution to who committed the murder, and then you always pick the one with the least amount of assumptions, right? So that is what's called as the Occam's razor, and so on. So there are lots of cases where optimization occurs in practice. Science, right? So computer science is discrete optimization all the way, right? So you have a traveling salesperson problem, you have a graph, and then you want to visit all the nodes of the graph and come back in the least amount of time. And how do you do that? So that's an optimization problem. It's a discrete problem though. So there are so many examples of optimization. So, and now what we will be interested in this talk is how do you do this optimization, right? So that is what is more interesting. So these are all problems that we would like to solve, and the question is how do you solve it, right? So here I'm going to give you a very, very high level introduction to some of the ideas in optimization, continuous optimization. So to set an example, let's start with a hungry cow, which is at a position 2, in your x-axis and y-axis. It's like a two-dimensional cow, let's say, and it's in a position 2, in an open field, and the cow is tied to a rope which is 1 meter long or 1 unit long, whatever unit you want to consider, right? And there is some grass at position 4, 3 on the field, and now the cow wants to get, okay, there's some more. There's a perpendicular electric fence that passes through some point 2.5, 2 in this case, and now the goal of the cow is to get to the grass, but then it probably cannot get to the grass itself. But then the question is, how close can it get to the grass? As a picture, let's say this is the x and y axis. This is a two-dimensional cow, which is at this position. It's tied to a rope, which means it can only go in a circle until with a radius of 1 unit. And then there is a grass here, and you have a perpendicular fence. Now the question is, how close can this cow get to the fodder? What's the answer? What's the answer to this question? How about solving this question? Anyone? What are you trying to optimize? Distance from what? The cow to the grass, right? So, and what constraints do you have while trying to optimize? Of course, sorry, it cannot cross the red line. What else? Right. So this is an optimization problem. So you want to minimize the distance between the cow and the grass. At the same time, you have certain constraints associated with it, right? So you cannot. Somebody said you cannot go beyond the red line and so on, right? So what do you want to find? Want to find the position of the cow. Let x comma y be the solution. And what do you want the solution to satisfy? The solution should minimize the distance to the fodder, and then what restrictions does the cow have? So it has a rope restriction, so it cannot go beyond what the distance that the rope will allow it to travel, and it also has a restriction as to what the fence restriction, right? In x-axis, it cannot go beyond 2.5. So this is how you typically set up an optimization problem, right? As simple as that. So you have certain objective to solve, in this case, the distance to the grass, and then you have certain constraints, which in this case are the rope and the fence constraints, right? So this is the general framework. You have certain variables that you want to solve. In this case, the variables are your position. That's what you finally want to get to. That's the answer that you're looking for. The variables are x and y. And there is an objective that you want to solve, the distance from the grass. There are certain constraints. And you want to minimize or maximize the objective to solve for certain variables. And then you want to get with certain constraints that you have. So this is the general framework of optimization. Easy, right? So question is how? How do we solve it? Right? So here is how you do it. So let's consider the case where the cow is not tied to the rope, the easy case, and there is no perpendicular fence. Right? So then what's the answer? What is 0? Yes, the distance of the solution is 0, right? Because it can indeed get to the grass. So that's easy. So let's give it a twist. So let's say the cow does not know where the grass is. If it knows where the grass is, it can of course go and get to the grass. What it knows is, given a position, it only knows what's the distance of this position to the grass, right? So you can think of your objective as a black box. You feed in a number, you feed in a position to it, and then out comes an answer as to how close are you. What's the current distance to this grass? Right? So think of this as a blind traveler going and asking people, so where I am here, so how far am I to this position where I want to reach? And somebody gives you an answer, right? So that's all you have in general, because if you know where the answer is, you can always get to the answer, right? So that's easy, right? So that's typically not the case in real world problems, right? So you don't You know you want to minimize this, but you don't know what the answer is, of course. In this case, I told you where the grass was. Right? So what you can do is the cow can start at a random position. So the cow starts at 2, 2, and it knows how close it is to to the grass. So it will just put x and y, plug in x and y as 2 and 2, and it gets an answer. So it jumps to a different position, let's say, and now it gets a different answer. So it can keep doing this, right? So will this work? So is this a principled way to solve this problem? Not really, right? So what would be a principled way to solve this problem? And you know the distance to the place where you want to get to. You don't know the place, of course. You know only the distance. So what will you do? So you want to move to a next point, and that point should satisfy certain property, right? So what property should that point satisfy? Yeah, so if it is closer to the final solution than where you are now, then you can go in the direction, right? So basically the whole of optimization is about finding a good direction in which you want to move, right? If you have a good direction, then you can keep moving in this direction and hope that you will eventually go to the right answer, right? So it's as simple as that, right? So this is a key question in optimization. How do you find a good direction from where you are right now, right? So if you know the direction, as you said, you can always keep moving in that direction and get to the optimal. But how do you get this direction? That's the key question. So let's take a simpler example. So let's say you want to minimize this one-dimensional function. So just f of x is y, and it's just x squared plus 2. And let's say you want to find the x that minimizes this. What's the answer? Which x minimizes this curve? That's what I'm asking. 0, right? So that's the answer. So but let's say you start with 0.8. Right? This is a one-dimensional problem, right? So you start with 0.8. You have certain value for it for your y. Which direction should you move so that your value gets lower? So there are how many directions are possible now? What are these? Left and right, right? And in this case, is left a good direction or right a good direction? Because left is a good direction. So of course you can move to the left, right? So let's say I move to the left and go to minus 0.5, right? So and now what is a good direction in this case? The right is a good direction, right? So now given this function, right, you have this function. So you were at 0.8 and you said left is a good direction to move. You were at minus 0.5 and you said right is a good direction to move, right? So what about this function characterizes moving in the left or right, right? So this has to do something with the function, of course, right? If I gave you a different function, the directions are completely going to change. This left and right for this point was specific to this function, right? So which means somehow you have to use the properties of the function to get this direction, right? So now what property of this function can give you that? Function is this increasing or decreasing? So how does that help? Which point? We are on the left side or the right side of that point. Well, if I gave you that point, you know the answer already. You can find the slope. Right? So you can find the slope, and the slope kind of gives you some information. That's what he's saying, right? So what's the slope? So in general, it seems like in this case, you don't even want to know the slope. You can just look at the current value of x. If it is greater than 0, you move to the left. If it's less than 0, you move to the right. It's as simple as that, right? But how is that related to the slope in this case? Surprisingly seems to be related to the slope, right? So I can now have a simple algorithm. Forget the slope for now. Let's say if my current x is greater than 0, then I move to the left, and that will be my new mu x. If my current x is less than 0, then I move to right, and that will be my new left. So I'm going to add some d to the current x depending on where I am, whether I'm in the positive side or the negative side, right? So and what should this d be? What kind of a value? This d is a number, right? So what kind of number this should be if your current x is greater than 0? it should be a negative number. And if its current x is less than 0, this should be a positive number, right? So that you move closer and closer to 0, depending on which direction you are, right? So this is what we want. So we want your current x is greater than 0, we want your d to be less than 0. And if your current x is greater than 0, you want your d to be greater, other way, right? So current x is less than 0, you want d to be greater than 0. How can you find a d? Right? Somebody suggested slope, right, which is the derivative. So we can look at the derivative of this function. What's the derivative of this function with respect to x? 2x. Okay, so how does that help? So if x is positive, what is 2x? X is negative, 2x is negative, but what we want is the other way, right? So if x is positive, we want d to be less than 0. If x is negative, we want d to be greater than 0. What can you do? How does the derivative help? Exactly, right? So the derivative is always gives you the current. I mean, if current x is positive, derivative is also positive, and you move in the negative direction of the derivative, and you get what you want, right? So that kind of solves the problem in this case, right? So what's the derivative of x? The negative of the derivative does the trick, as somebody mentioned, right? So, okay. So let's say if we take this example, you are in current x 0.5. What is the negative of the derivative at 0.5? Negative of the derivative at 0.5. Careful. What is the negative of the derivative at 0.5? It's minus 1, right? Okay, so good. So somebody said move in the direction of the negative of the derivative. I'm going to do that, right? So I add negative of the derivative to this. I start from 0.5. I subtract 1, minus 1. I go to minus 0.5. What's the negative of the derivative at this point? 1. Okay, so now I add the negative of the derivative to minus 0.5. Where do I end up? I end up at 0.5. So am I getting, will this solve the problem now? What is the issue? Derivative is changing at each point, otherwise you won't find a good direction to move. The derivative better change at each point, right? Otherwise you are always moving the same direction, which you don't want. If you started in the negative and the derivative showed the wrong way, then you have a problem. But what you mentioned was right. So what was that? Yeah, it keeps oscillating between minus 5 and 0.5. You'll never get to 0, right? So you essentially you are moving in the right direction, but you're moving too much, right? So you jumped above. So you wanted to get to 0, but then you jumped over it and you went to the other side, which is a problem. So how can we solve this problem? Multiply what by a small number? Very good. So what you are suggesting is you start from a point, the negative derivative somehow magically, we don't know why, gives you the right direction to move, and then you move as little bit in the negative direction, and then hope that that works, right? So that's what the algorithm that we have for optimization right now, right? So that's what is called a step size, as some of you said. So you want to multiply it with a small number. Small, how small is a question, right? So because in this case we multiplied it with 1, maybe you want to multiply with, well, 0.9 is still might be a problem, right? So we have to see what gives you the right answer. So the question is, I will let you think. So there are lots of questions that I will leave you with, so which you can think during the talk or later after the talk. So one of the questions is, how should you modify the step size to avoid this problem? So you know that you have to multiply it with a small number. Does all small numbers work? So should you choose it in a certain way and so on? Are there problems where some fixed small number is not going to work? Think about it. Okay, so here is the algorithm, the basic algorithm. You now know, actually you constructed yourself the basic algorithm of optimization. It's called gradient descent. The algorithm is this: you start at a point, find the gradient at that point. Gradient is nothing but the derivative in your one dimension. So that's the higher dimensional derivative. And then you move in the direction of derivative a small amount and then repeat, right? And this algorithm need to go to a minimum or maximum, depending on what you want to do. In this case, it's minimum, yes. Right, so negative of the gradient at this direction at 2, 2 for this curve. Well, in the case of 2 dimension, the gradient is what? So in this case, Yeah, the gradient is it's a two-dimensional vector, right? It's not a number in the last we saw in the last time, right? So that's why the gradient gives you a direction to move. So in the at 2 comma 2, the negative of the gradient is 4 comma 2, which means it's pointing you in this direction. The grade then, irrespective of where the curve starts, interestingly, the negative of the gradient always points towards the grass, right? So you can always rely on that direction to move. That's what this algorithm uses. That's the key insight from this algorithm. Yeah, so if the curve is here, then the negative of the gradient points again towards the grass, right? So which is interesting. So here are 2 points. The gradient descent is the simplest unconstrained problem. We still haven't tied the curve to a rope. We still haven't put the fence. We'll come to all that. But this is the unconstrained. There are no constraints to this problem. And if your step size is chosen properly, the amount you have to move in the direction of the gradient, this algorithm will probably converge to a local minimum. Here's a question. So I'll tell you that the gradient descent does not always converge to a global minimum. Why would that be? Exactly, right? So what's a local minimum and what's a global minimum? So can you think of a function which has a local minima as well as a global minima? Do all functions have local minima and global minima to be different? So can a function have more than one minima, first of all? Why? What kind of functions have more than one minimum? Sine functions. So you have to be careful here. So when you say the value of the minimum, it's the same, right? It's the x-axis that is different, right? Somebody said sine function, it has multiple minimums. Would you call these minimums as local minimums? So is this the smallest that you can get when you do a sine function, right? So when you're looking at the bottom point, this is the smallest of the whole function, right? It's still a global minimum. What's a local minimum? What could be a local minimum? So here is a function. This is a different sine function. This is so which one is a local minimum? Which one is a global minimum here? So how many local minimums does this function have? 3. And how many global minimum? Okay. So here what I'm saying is the gradient descent might not always converge to the global minimum. So would you guys agree? And why is that? On the starting point, right? So if you start in the right point and then your gradient is going to point you towards the global minimum. But if you start in the wrong point, it's only going to point you towards local minimum. So what this kind of says is that the gradient is not really pointing you towards the global minimum, but only giving you a direction of immediate decrease, right? It's only giving you a direction in which if you move a little bit, your function is going to decrease, which means if you start at the wrong point, then you end up only in a local minimum. Okay, that's a good observation. So this is an easy question. How do you modify the algorithm gradient descent to find a local maximum instead of a minimum? Sorry? Somebody said something. Add what? So just move in the direction of the gradient as opposed to the move in the negative of the gradient, right? So if the negative of the gradient is going to point you in the direction of decrease, the gradient itself will point you to the direction in which the function increases. So you can just add the gradient and you can repeat the same thing with the proper step size. It's going to get you to a local maxima. Again, you cannot go to a global maxima, but you can go to a local maxima. Good. So there are lots of other methods. So a whole of optimization, a lot of optimization, continuous optimization is about picking this direction in which to move. Gradient was something that you guys came up with, but then there are people have thought about other interesting directions in which you can move as well. So I'm not really going to talk about that. So I'll let you think Are there other interesting directions given a point which will allow you to maybe get to the minimum faster? That's a question for you to think. Okay. So this is the summary of gradient descent, which this is the first one that I wanted to say. So here is some recap from your maybe high school. So how many of you remember this? The Taylor series expansion. And I have less time to spend on this. What is the Taylor series doing? So what is it trying to do? What does this formula, complicated looking formula, actually giving us? Sorry? Approximating what? X plus epsilon d. It's not so. So this formula looks first of all tricky, right? So I put a plus dot dot dot. What are those dot dot dots there? Infinite number of terms that I can add here. So which means it's not really an approximation. If you add all the infinite terms, then this is an actual answer, right? So let me tell you what this exactly does. You guys are right. So you take a function and try to find the value of that function at a point x plus epsilon d, right? So if you, this should remind you of what we do in gradient descent, right? You start with x and then you move epsilon in a direction d. So this is a new point. You want to find the value of the function at this new point, and the Taylor series says, well, you don't want to know anything about the new point. You can completely know the value of the new point by knowing information at this current point only, which is interesting, right? So all this on the right hand side uses the function values are all evaluated at x, right? So you can find out the value of x at the point x plus epsilon d only using values at x. But what are these values? These are values that depend on x, f of x, f dash of x, which is the derivative, f double dash of x, second derivative, and so on. If you knew all the derivatives of a point at a given point, then you know everything about the function. That's what this is saying. You can evaluate the function at any point that you want, any x plus epsilon d, right? So that's what this is saying. So which is kind of interesting, right? So you have total control over the whole function by knowing information at a given point. That's what this is kind of saying, right? When epsilon is really small, which is the case that we'll be interested in, because we're going to move a very small bit in a particular direction. For a small enough epsilon, what is this saying? So x plus epsilon d, the value of f at x plus epsilon d minus f of x is approximately something like the first term here, right? So if you put bring f of x to this side, your first term is epsilon d f prime of x, right? It is approximately epsilon times d times f dash of x. So now the question is, well, so you want a new point, the value at the new point to be minimum, right? So you started with f of x, you want this to be less than f of x, then you are moving in the direction of decrease, right? So then the new point is a good point because you want to minimize this function. When will this be minimum? When this guy is negative, right? And when will that guy be negative? When your epsilon is your step size, you want to move certain amount, so that's positive. The only way this can be negative is when your epsilon d f prime of x is as small as possible, right? So now the question now is how can you make epsilon d f prime of x as small as possible by choosing a good d? What d gives you that? Who did we choose? We chose the negative of the derivative was the d last time, right? And what is the negative of the derivative? It is just minus f prime of x, right? So if you put minus f prime of x, so the value is going to be minus epsilon f prime of x squared. The squared is a positive number, epsilon is a positive number, you have a negative. So that is guaranteed to give you a decrease in that direction, right? So that was the rationale why choosing negative of the derivative was a good idea, right? We saw that in the previous small example, it seemed to work well, but then this is why it is indeed working well, right? So that's why negative of the gradient is a good idea. So it is in fact giving you the maximum value. It is giving you the maximum decrease. That can also be shown, so I won't really do that. But the important point you have to consider here is any d such that d into f prime of x is less than 0 is a good direction. Are you guys with me, or are you all already lost? Right? So I'm trying to move in a direction, and I want this guy to be negative. I decided that to put minus f prime of x. Yes, that gives a negative value. But then the observation from the Taylor series is that not just the negative of the derivative, but any d such that d times f prime of x is less than 0 is a good direction of descent. Right? It's a negative direction. It's a direction in which the function reduces. And we'll see how this will be useful as we go along. Jumping to function of many variables. So this is the most interesting case. You are never going to optimize a single variable. So you're always going to you'll always be given billions of features, and then you want to optimize price and so on. So you'll always have multiple variables to deal with in real world. So this is a direct Taylor series expansion in multi dimensions. So what you have is bold x's, boldface x's, which are not a single number but a set of numbers. So this is kind of a vector now, and d is again a vector. If you remember the cow example, when it was in 2 2, it was pointing in direction of 4 2. It's called a direction because it's not a number; it's a vector, and vector has a direction and a magnitude, right? So it's a direction. So that's what this is. The analogy to the previous, exactly like the previous slide, is that okay. So here is one more thing that you want to know. Here is, instead of d into, so instead of multiplication, what you have in multivariable calculus is transpose, right? So the d transpose del, which is the gradient, which is like the derivative. Think of it as a derivative. So if there are two vectors a and b, and then you look at a transpose b, it's just the sum of the products, right? So that's how this equation looks in the multidimensional case. What does this mean? It means any direction such that d transpose your derivative less than 0 is a descent direction. Of course, you can again take the negative of the derivative, which is minus del of f of x, which will still be a descent direction. But what does this mean in pictures, right? So you have del f of x, which is, you are at this point, and then your gradient points in this direction, right? What does this red line satisfy? What equation does this red line satisfy? So what is the relation between the red line and the green line? It's perpendicular to that. What does that mean? So you have a vector del f of x. Yeah, but can you give me the equation of this line? That's what I'm asking. So you take any point d in this line. What is d transpose f of x? Okay, so it's 0. So this is the set of, so if this were, think of this point as 1, 1, right? So, and what is the equation of this line? Set of all points which satisfy x plus y is 0. Right? So that's any point there is a scale of 1 minus 1, right? Minus 1, 2 minus 2, and so on. Right? Then you take any point here, do a dot product with this, you'll get a 0, essentially. So fine. So you have a direction. So what this is saying, you have a vector, and then the perpendicular line is just d transpose derivative of 0, right? So what can you say about any direction on this side? What would that satisfy? If this was 0, what should this be? This should be less than 0, and the other side should be greater than 0, right? So what is this essentially saying? So right? So you can choose to travel, if the curve is in this point, and if this is the gradient towards the grass, I mean, this is showing the value of maximum increase. So the grass is somewhere here. What this condition is saying is that you can travel in any of this direction so that the function itself will reduce in that direction. By how much and so on is a different question, but then you can reduce that function in that direction, right? It's a descent direction. Yeah. So why have we taken the okay, so the transpose, so this is just, you can think of this as giving some weights to the partial derivatives in each of these directions, basically. So the transpose itself comes from the Taylor series expansion, basically. So this is the generalization of your Taylor series to multiple variables. So if you want to find the value of f at x plus epsilon d in a particular direction, then the Taylor series says it exactly depends in this fashion. right? So you want to see how much, okay, so that would need some explaining, but probably I'll skip that. So right now it's kind of saying that how much component of D is in this direction of f of x. That's what is kind of capturing. But for now, for this talk, assume that if the transpose is 0, then it just means it's perpendicular. If the transpose is less than 0, it's on this side of the hyperplane of the line. If it's greater than 0, it's on the other side of the line. That would be enough for this talk. So I'll explain more maybe offline. Okay, so why is this useful? All this machinery we are building up is useful because we want to do constraint optimization, right? So this is the norm. So whenever you have a problem at hand, so in practice it's always constraint optimization. It's never unconstrained. You will never optimize for your price without certain constraints, right? You have certain budget. It always comes with a budget. That's a constraint that you have, and so on, right? So what is the constraint optimization problem that we'll start looking at? So you have to minimize something such that some other constraint is satisfied, right? Such that in this case, let's say there is a different function g of x, which is 0. That's the optimization that we care about. So we'll define two important things for constraint optimization. Given a point x, we'll look at two different things. There is a direction which we'll call as descent direction, and there is a direction which we'll call as feasible direction. A descent direction is you are at a point and you want to minimize a function f of x. That's your goal, right? So at this point, every direction in which f of x reduces is a descent direction. You can move in this direction so that you can reduce f of x, right? So this is the descent direction. But what's a feasible direction? Any direction such that in that point you are still satisfying the constraint direction, right? So you can move in a direction, but then if your constraint is not satisfied in this direction, there is no point in moving in that direction, right? Because finally you want to minimize it subject to certain constraints, right? So now here's a question for you. I give you a point and claim that this point is the minimum of this problem under these constraints. Now, how will you verify this is indeed the minimum? So with respect to the descent and the feasible directions. Sure. So in other words, so let me ask you this question. So what kind of descent directions can this point have, which I'm claiming to be the minimum, right? So descent direction, which is also feasible. So descent direction is where the function reduces. Feasible direction is where the constraint is satisfied. If I give you a point and claim that this is the minimum under these constraints, but then it has a descent direction which is also feasible, what does that mean? Exactly, right? So if there is a descent direction which is feasible, you can always move in that direction and reduce the function further because it's a descent direction and still satisfy the constraints. So this point cannot be the minimum. So the basic thing that you want to check in constraint optimization is there should not be any descent directions which are feasible. As simple as that, right? So is that clear? Okay, so how do you check that in pictures is what we'll do now. We want to see, let's say you start at point some x star, somebody claims that this is the minimum under certain constraints and this is the direction in which the derivative is. This is where the descent direction is. So which means, this is where the derivative is, which means all these directions are descent directions from whatever we saw earlier, right? So this is there are places where d transpose del f of x star is less than 0. So these are the directions. When I say directions, I mean I can move x to here, here, somewhere close by such that the function decreases in that interval. All these directions are feasible directions. Let's say this is my gradient of g. Gradient, this is the derivative direction in which the constraints derivative is, right? So what does this mean? This means this of course is think of this as a tangent to the to where the constraint is actually 0. So it means, let's say there is a curve like this for which g of x is 0. Now it's just think of this as the curve where g of x is 0, right? So now is there a descent direction which is also feasible? If your green line were all the feasible directions and your that red thing were all the descent directions, if these were all your descent, these were all your feasible, then is there a descent direction which is also feasible in this case? Yes? Which direction would that be? Can I move in this direction and claim? No, right? So I can move in this direction and claim that, well, in this direction, it's a descent direction, and this direction is also a feasible direction, right? So this point better not be the minimum, because I can always go to a different point where it is minimum, right? So this x star is not the answer to this problem. So now what is this suggesting? So how can you relate the gradients of the function, the objective and the constraints, such that you will not have a descent direction which is also feasible? In other words, how should this red and green line look like? Why should it, somebody said overlap, why should it overlap? Okay, let's see how it looks like if it overlaps. So now what happens? So now, as you said, so this is the del f of x. So these are all descent directions. Remember, on the line it's 0. Only if you come to this direction, it's less than 0. But when del g of x is also in this line, then your green line is exactly overlapping with your red line. And that means you don't have a descent direction which is feasible, right? So now what we have done is we have taken a function and put some constraints and figured out what is the necessary condition for a descent direction to be also feasible, right? So that's what we have done. And how do you write these constraints? How do you relate these to del f of x and g of x, del g of x? Mathematically, how would you put it? What's overlap even mean mathematically? Shout. Can't hear you. The angle between them is 0, which means, sorry? The dot product is not 0, because if the dot product is 0, they are perpendicular. Fine. So the simpler way to say this is, so what happens if del g of x was on this side? They don't overlap now. Is it still okay? Still okay, right? Because your descent directions are those on the green line, right? So the perpendicular line does not change. So what does this mean? This means your del f of x should be on the same line. That's all you're wanting, right? But they need not be on the same direction. Just means, right? So this is the conventional way of writing it. So your del f of x is equals del g of x. That's what you would want, but then it can be scaled by some value, because if I scale g of x to whatever in this direction, the perpendicular line is going to stay the same. There is some scaling factor that can be there, but then the directions are the same, or they can be different, right? So your lambda can be any value. If it is negative, then they are in the same direction. If it is positive, then they are in the opposite direction. But that's fine, right? So now this lambda has a special name in optimization. It's called the Lagrange multiplier. So this is something that was, so this insight was something invented by a famous mathematician called Lagrange. So it's named after him. So this is for constraint optimization, where we saw g of x equals 0. So now we'll quickly see the case where your constraint is much more. Your g of x is less than or equal to 0, and I'll finish with that. So what do you do? You again have this x star, and you have a descent. You have a gradient in this direction. These are all your descent directions, and now you have del g of x star the same. So now what are your descent directions in this case? Be your descent direction in this case. Last time g of x was 0, so we only said the perpendicular line is your descent direction. But now you want g of x less than or equal to 0. So which are the directions in which you can move so that you can reduce g further? You can do this, right? So any of these directions are fine, right? So now, is this a minimum point? Same argument that we did before, right? Because there are so many directions now, not just the green line, but there is a suite of directions. You can just take the intersection of these two uh, hyperplanes, and that is going to give you all the directions that you need. So now, what happens in this case? So this is a good case, right? So now, is this a good case? So now, do we have a descent direction which is, we still have, right? So we can still go in this direction of the red arrows and still, I mean the red area, and still reduce the function and also reduce the constraint. So this, we still have a descent direction which is feasible, right? So this is still not an answer. What about this? Now you're okay, right? So now these two descent direction space and the feasible direction space do not intersect. So which means this point does not have a descent direction which is also feasible, which means it could be the minimum, right? So now how do you mathematically represent this? The only difference between last time was, last time you allowed both directions for del g of x. It could be parallel or anti-parallel. Now you're saying only it should be anti-parallel. So how do you exactly, excellent. So you want minus lambda, it's the same equation, just that lambda should be positive. That's the only difference that you have when you put this equality constraints into it, right? So it's still called the Lagrange multiplier, and this is pretty much the foundation for understanding optimization, constraint optimization. So so the only constraint you get here is lambda is greater than 0, right? So I'll also let you think. So what we have just said was, if you have a descent direction which is not feasible, then if you have a descent direction which is also feasible, then the point cannot be minimum. But can there be cases where you don't have a descent direction which is not feasible, but still the point is not the minimum that satisfies this constraint? In other words, I'm asking, is this condition or is it also a sufficient condition? Given this point, we know it is necessary for no descent direction to be feasible to exist. But then if I confirm that, okay, there is no descent direction which is also feasible, then can I be sure that this point is the minimum? Well, I'm okay with the local minimum as well in this case, because it's hard to find the global minimum for most problems. There may be no minimum. So if there is no minimum, can this property be satisfied? If there is no minimum, which means the minimum is minus infinity, let's say, then there should always be a descent direction. Means what? So let's think a bit about that. So what does no minimum even mean? When there is no minimum, it means what you are saying is, irrespective of what point it is, there is always a direction, descent direction, which is also feasible. That's what it means, right? So in this case, we have confirmed that there is no descent direction which is also feasible. But I'm asking whether that means it has to be a minimum. I'll let you think about this. The answer is no. So if it were yes, then we have, so this half an hour we have understood everything about optimization. That's all it is about optimization. But unfortunately, the answer is no. So it turns out that checking descent direction to be not feasible is only a necessary condition. There are functions for which there are points where you don't have descent directions which are feasible, still it may not be the minimum. Those are called as saddle points, which means in one direction the function increases, in another direction it increases. So if you look at the horse's saddle, right? So if you look at the bottom point, in one direction it goes up, in another direction it comes down. Right? So these are points for which this condition is not sufficient to guarantee minimum. Anyway, all this for later. So I'll probably end here. Okay, what else? Okay, so this, so now one quick thing. So what does this mean? So we started off with this, minimize f of x such that g of x is 0. We said that is a condition that we want to satisfy. What this guy did, Lagrange did, was, so he said, well, if that is the case, you just transform your constraint problem to an unconstrained problem. Put your constraint in the objective itself, right? So now there is some lambda such that you add that lambda to your objective and g of x, which is your constraint, and solve for the proper lambda, right? In other words, it means that you are kind of penalizing how much you're going far off from your constraints, right? So this you want to minimize this whole thing now, right? But then if this guy is higher, so that's a penalty that you're paying for not satisfying this, right? So what we can show, I don't want to go into the details, but then these two problems are equivalent, right? You don't want to solve the constraint problem, you can solve an unconstrained problem itself. Right? That was the insight of Lagrange, and till date, this is how people kind of solve simple unconstrained problems. What did we not cover today is constraint optimization. We just saw one constraint. We just looked at one gradient and how they interact. So maybe you can start thinking about if you have two constraints, that is going to give you two different gradients, and what conditions should these gradients of the constraint satisfy so that you still don't have the same kind of descent directions which are not feasible. That is one thing we did not cover. We did not cover constraint optimization with either equality or inequality constraints. So there are these necessary and sufficient conditions, or what are called as Karush-Kuhn-Tucker condition. So the nice story is that Kuhn and Tucker were famous mathematicians who kind of proposed these conditions, and then they realized that 20 years or 30 years earlier, this man called Karush had given these conditions when he was doing his just finished his bachelor's and started his master's thesis. So what I'm trying to say is, so these things are very accessible to all you guys as well. So whoever has interest should definitely read more about this. There are certain types of optimization problems for which you can do much better than the simple gradient descent that we spoke about. These are linear programs which have certain types of constraints. Convex optimization is another big area where your function is what is called as convex. So we said there are some, in these cases, there are local minimums and global minimums. There are cases where if you have a minimum, it better be global minimum, right? So every local minimum is a global minimum. So these functions are called as convex functions. Of course, as you would see, these functions have more structure. The more the structure you put, the faster your algorithms will become, the easier you will solve it. Gradient descent is no longer the best way to use. So more sophisticated techniques have been developed, and there's something called as duality theory. So, which means which relies on the property that when you're in mathematics in general, not only in optimization, when you want to solve a particular problem, what you do is you look at a related problem which has the same solution as this problem, right? So it's called typically the dual of this problem, and in some cases the dual might be much easier to solve than the primal. And there are cases where that happens. I don't know if there is a machine learning course where they taught about support vector machines. So support vector machine is nothing but a convex optimization problem which relies a lot on duality, essentially. So convex duals, etc. There are much more. So this is not even the tip of the iceberg. I'm just saying there is an iceberg somewhere deep below. So that's all I've said today. So the summary, optimization is a very useful branch. Applied mathematics, not just computer science. If you are an engineering student, I would say it is mandatory that you understand basics of this, because philosophically life is an optimization problem in itself, right? So I think it's good to know a lot of these things. Very well studied, yet there are so many problems which are open. Now with big data, you have so much more data, and then all these problems require the factor of scaling. How do you make it robust? How do you make it scalable? How do you make it tractable? All those things come into picture. And if interested, we can definitely talk more. I am finishing early, but that's okay. Thank you very much. Any questions I can take? Thanks.
I think that you are talking about language, it can also.
Like how? What do you mean? How do you? Can you explain more? What? Mm-hmm. Yes. So essentially, you're saying that smoothing can be set up as an optimization problem, right? So you have certain pixels already, and now you want to fill the missing pixels. The missing pixels cannot be arbitrary. It has to satisfy certain function. So typically these functions are some rank function of the matrix or something. Yes, yes. I think there was a matrix completion talk sometime today, or was it yesterday? So Saneem gave the talk. It's over. Okay, so I think probably people have already spoken about it, right? So anything in image processing, machine learning, all are optimization problems, right? So because you want to make a decision, right? In this case, the decision is to get an image which looks smoother, right? So in some cases, the decision to whether give a loan to somebody or not, decision to I mean, a decision based on whether it will rain tomorrow or not, right? So these decisions are what? So you are essentially having some objective and you want to maximize your cost, maximize your profit or minimize your cost, right? So all these are decisions. And decision is the mathematical abstraction to translate decisions is this framework of optimization. So yes, yeah. So the answer is yes for that. Yeah. So that's a completely different beast. So continuous functions are easy to understand. Well, so easy to understand in this framework. So there are the discrete optimization is itself a big area. So you can look at things called integer linear optimization. For instance, so if I want to allocate people to jobs, I cannot say you put 0.3 per person, I mean 0.3 fraction of this guy in a job. That is not typically the case, right? So you want to put a 0 or 1. So these are discrete problems. So typically what there are certain problems are amenable to discrete optimization, certain problems are not. So in those cases, one of these ways they do is they kind of relax it to a continuous problem. So you want values either 0 or 1, you say maybe I'll make it 0 to 1 and then threshold it based on the answers that you get. So now the question is how good that is, that's a different question. So those are where the approximations come in, right, which is another field in optimization. You have a solution for a different problem. You want to solve an integer problem, you solve a continuous problem. Now, how good is that problem for this? So that is another area of algorithms which people look at approximations and so on. Yes, the answer is yes for that as well.
Stan, Arun, by the way, why did the chicken cost?